So the cross product is another operation that we can perform on two vectors, similar to multiplication. So it's like the dot product in concept, but we're going to see that the cross product and the dot product have very different properties. So given two vectors a and b, we can define their cross product using determinants. If you are not familiar with determinants, then you should review that before watching this video. So with each component I, j, and k, which remember are the x, y, and z components of a vector, we have a 2x2 determinant with different components from the vectors a and b. And so if we were to evaluate the determinants, then we would get the components like this. And so as you can see, it's kind of a big mess, and it is, but you'll get used to it after doing a few cross products. We defined it using 2x2 determinants, but notice that we can use a 3x3 determinant with I, j, and k in the top row. This is often used to help memorize how to do the cross product. You place I, j, and k in the top row, and then the first vector, and then the second vector, and then you take the 3x3 determinant. However, note that this is not an actual determinant because the I, j, and k are unit vectors, not numbers. In a determinant, you can only have numbers. So this is just something to help you memorize the formula. And so one difference from the dot product that you should have already noticed is that the cross product produces a vector because we have these x, y, and z components of the vector. While the dot product produces a scalar, the cross product produces a new vector from our two original vectors. And this new vector that we produce from the cross product is always perpendicular to both the original vectors. So for example, if vectors a and b were lying on a flat piece of paper, then their cross product would either be sticking straight out of the paper or going straight into the paper, because those are the two directions that are perpendicular to the paper. And we can see why this is true if we just take the dot product of A and the cross product, or of B and the cross product. And so it'll always be 0. So as I mentioned before, given any two vectors A and B, there are two possible directions which are perpendicular to both A and B. Again, if A and B are flat on the paper, then the cross product, the two perpendicular directions, are straight up or straight down, in and out of the paper. And so sometimes that is represented with these symbols. The X means it's going straight into the paper, and the dot means it's coming straight at you. So how do we know which direction the cross product is pointing in? So we can use something called the right-hand rule. So basically what it is you stick your thumb up, like in the picture, and you try to curl your fingers from A, the first vector, to the second vector. Imagine vector A rotating to vector B. So in this picture, I drew the arrow that A would rotate to get to B. You always want to go through the smallest angle possible. So if you curl your fingers in that direction of rotation, then your thumb would be pointing into the paper. So that's the way the cross product would be pointing. So now we can look at some of the properties of the cross product. So first, if one of the vectors is multiplied by a constant, some constant c, then c is going to pop up in every term of the cross product, so we can just factor it out. So that's the same thing as c times a cross b. We can move any constants out of the cross product just like with the dot product. Now, if we have B cross A, then to get that, we just have to look at the formula and switch the A's and B's. And so we find that it's the negative of A cross B. The commutative property does not hold for the cross product. A cross B is the opposite of B cross A, meaning they have the same magnitude but opposite directions. The distributive property does hold for a cross product. So if we have A cross in parentheses B plus C, then that's the same thing as A cross B plus A cross C. And then lastly, if we have a combination of the dot and cross products, then we can kind of switch the positions of the cross and the dot. But notice that the parentheses have to move with the cross product, because A cross in parentheses B dot C does not make sense, because B dot C would make a scalar quantity, and we can't take the cross product of a vector and a scalar. Only two vectors can do that. So now we find a relationship between the cross product and the angle between the vectors A and B. Just like how we found that the dot product of two vectors A and B is equal to the magnitude of A times the magnitude of B times the cosine of the angle between them. So if theta is the angle between the vectors, and this angle can be between 0 and pi, then the magnitude of the cross product is equal to the magnitude of A times the magnitude of B times the sine of this angle. And the proof of this is very long and tedious, so I'm just going to start from the end of the proof. So if you want to, you can check that this equality is true. The magnitude of the cross product squared is equal to the magnitude of A squared times the magnitude of B squared minus the dot product of A and B squared. And then we can replace the dot product with, remember that formula that relates to the cosine. And then factoring out the magnitude A squared, magnitude B squared, and then replacing 1 minus cosine squared with sine squared theta. And then now you just have to take the square root of both sides to get the formula. Okay, so let's look at the geometric significance of this equation. So let's say we have these vectors A and B, and we draw a parallelogram with them. So what is the meaning of the magnitude of the cross product? So we know that the actual cross product is a vector sticking out of the page or into the page, but we find that the magnitude of the cross product is going to be equal to the area of this parallelogram that we make with the vectors A and B. Because as you can see, the height of the parallelogram is equal to sine theta times the magnitude of A. And so according to our formula, the height times the base is just going to be the magnitude of the cross product. And so remember how if the dot product of two vectors is 0, then that means they are perpendicular. Well, if the cross product of two vectors is 0, and the two vectors aren't 0 themselves, then that means the sine of theta must be equal to 0. And so if sine of theta is equal to 0, then the angle between the vectors must be 0 or pi. And so that means the vectors are parallel or anti-parallel. Anti-parallel just means they're parallel, but they're pointing in opposite directions. That would be if theta is pi. So to check if two vectors are perpendicular, we use the dot product. And to check if two vectors are parallel, we use the cross product. And so lastly, if we add a third vector into the mix and form a 3D shape like this, called a parallelepiped. So it's basically just a 3D parallelogram, In the diagram, you can see that the vectors C and B form the base of the parallelepiped, and then this vector A is one of the sides pointing upwards. So the volume of this shape is going to be the area of the base times its height. And well, we just learned that if we take the magnitude of the cross product of two vectors, it gives us the area of the parallelogram that they form. So that means the area of the base of this shape is going to be the magnitude of the cross product of C and B. And so if you look at the diagram, you can see that the height of the shape is going to be the scalar projection of A onto their cross product. The actual vector cross product, not just its magnitude. Because remember, the cross product is always perpendicular to both C and B. So it's going to be pointing straight upwards. And so the height of this shape is the cosine of that theta, where theta is the angle between A and the cross product, times the magnitude of A. And remember a formula for scalar projections, which you just get from the dot product formula. This is the same thing as A dot, the cross product, divided by the magnitude of the cross product. So putting these together, we can cancel out the magnitude of the cross product. Notice how, even though C cross B and B cross C are not the same vector, they have the same magnitude. So we can cancel them out. And so the volume of this parallelepiped will be A dot, the cross product of B and C. So to recap, given two vectors, if we take the magnitude of their cross product, we get the area of the parallelogram that they form. Given three vectors, where B and C are the base of the shape, and A is one of the diagonals, then A dot, the cross product of B and C, is the volume of the parallelepiped.